Our next speaker is Melissa Battler, who will be talking on Autonomous Soil Assessment System, Contextualizing Rocks, Anomalies, and Terrains in Exploratory Robotic Science. And of course, there's an acronym, ASAS-CRATERS.
Great, thank you very much. Let me just get my slides here. No, you don't. Now you do. All right, I'm hoping this is working. So good morning or afternoon again. So my name is Melissa Battler, and I'm a planetary geologist and the Chief Science Officer at the Canadian Space Exploration and Robotics Company, Mission Control Space Services. And at Mission Control, we develop computing solutions that support planetary science missions by enabling onboard and offboard autonomy, and thereby streamlining mission operations. We test and validate our software through analog missions as well. So I'll mention that my co-author, Kaisa Bremelwala, who's an engineer, is listening in and can also help to answer if there are any more engineer-related questions at the end too. So today I'm going to talk about the science autonomy tool that we're developing for lunar exploration. And as mentioned, it's called ASAS-CRATERS. Although I will talk largely in the context of robotic exploration, I will touch on Artemis as well in the last couple of slides. So as several speakers discussed yesterday, science operations in the new paradigm of commercial lunar missions, as well as Artemis, will differ in significant ways from any previous planetary missions that we've experienced. Mission operations teams and science backrooms will face new challenges, and early robotic missions will be short in duration with limited onboard autonomy. There will likely be a lot of data generated on board, which will need to be triaged, and there will be a highly constrained downlink capacity. Tactical cycles will need to be rapid and may even include real-time live streaming of data rather than the punctuated downlinks that we're a little bit more used to in planetary operations. In any case, decisions will need to be made very quickly due to these short durations and short turnaround time. Analyzing terrain in backrooms can be time-consuming and relies on downlinked imagery that may be, in these cases, compressed or downsampled due to bandwidth or downlink restrictions. Additionally, it can be difficult and sometimes serendipitous to quickly catch novel features or features that may have been seen before or are rare to find. So in this new commercial paradigm, delivery and operations companies face pressure to maximize scientific return and to lower costs. These are challenges that we embrace because ultimately we face the risk of needlessly leaving data behind on the moon, and no one wants that. So this is what's driving the demand for more onboard autonomy. To address these challenges, we're developing an onboard science system, which is called ASAS-CRATERS, and it's designed to support and aid lunar scientists during mission operations through autonomously classifying terrain. So in its current design, a couple of algorithms will run on board. So as a rover or even an astronaut moves around and captures standard RGB imagery, our algorithms will perform terrain classification and novelty detection. This happens at a rate of about 1 hertz. So these algorithms are based on deep learning models, which are informed by our science team. So we've previously developed and field tested our terrain classifier to TRL5 for the Mars analog study SANDY, which was deployed in Iceland last summer, and this is part of the NASA P-STAR program. To provide a little bit more of the scientific context, so a few examples of the types of lunar-specific terrains or terrain features that we're able to autonomously classify are rock fields, regolith tone, hills, craters, the different features of craters, including crater size, crater freshness, crater fields, and more. So the scientific rationale for, say, crater freshness is that crater freshness relates to the age of the crater. So by examining craters with different degrees of freshness, the way in which the lunar surface ages can be better understood. One more example, so crater fields provide insights into the timing and mechanisms of the moon's bombardment history. So craters of similar size and alignment relative to larger crater, as we know, could be consistent with secondary craters So such crater chains could provide access to materials from different regions of the moon. So being able to quickly and autonomously kind of identify like, hey, look here, this is a feature of interest, might help to address some science goals related to that. Additionally, a variation in the tone of Highlander and Mare terrains in regolith can be useful to help pinpoint areas of interest for determining variations in composition and age. So yeah, by quickly doing this, we can hopefully buy science teams a little bit more precious time to be able to take a more in-depth look at the features that are of interest, or to perhaps request higher resolution images where only compressed images have been sent before. So on the side of novelty detection, we're considering approaches to deal with known features that are relatively rare, such as, say, pyroclastic deposits or outcrop, or even a meteorite, as well as anomalous looking features based on morphology and coloration. So I've shown on the slide here some examples from previous missions. So beyond this, we're interested in exploring the use of other cameras, how our classification technologies can be used with multispectral cameras or remote or micro imagers to get a deeper classification of mineralogy and composition. Our system can also then project the results to the ground plane to aggregate data onto uniform mapping tiles. And this can hopefully provide context and scale and make it easier to analyze results using GIS tools. Once we finish prototyping this year, our next goal is to build an application to enable autonomous instrument targeting and potentially also downlink prioritization. So overall, these data products are compact terrain representations that can be more efficiently downlinked in tight operations scenarios with limited time allowed at any given stop for science data analysis due to mission constraints. They can potentially aid backroom operations in a number of ways. First, by allowing for faster analysis of imagery. Second, by detecting these novel features that a human operator may miss due to the demands of these rapid tactical cycles. And also by allowing for easy integration into GIS tools to allow for, say, overlays with orbital data or whatever else. And additionally, when used on board the rover, our algorithms can additionally boost science operations by maximizing what can be observed in compressed low quality imagery. So say, for example, the science team is only in a given scenario able to receive these really compressed images, while on board the rover, these algorithms can run and kind of in like a low file size sort of compressed way, still be able to convey some of that really important information.
8 minutes.
Thank you. And by allowing for the autonomous targeting of science instruments and cameras, supporting autonomous navigation of targets of interest as well. As a software-focused company, we're partnered with Cyphos Technologies, a leading provider of flight-qualified embedded systems. So together, we can offer the solution integrated onto a commercial off-the-shelf computer that has a low cost and low size, weight and power profiles, high-performance computing to enable state-of-the-art technology like deep learning. So it's a multi-mission system designed to be an auxiliary payload component that can be easily integrated onto your mission or lander-based payload suites, or potentially even into an astronaut suit. As a computer, it can be reprogrammable in flight to some extent as well. Right now, we're engaged with several delivery companies that are close to securing flight opportunities to demonstrate the system in 2022 and 2023. Ultimately, this has to meet the needs of scientists and their payloads, so we are eager to get inputs from everyone and the wider planetary science community on how this can be integrated onto different missions to offer the benefits of science autonomy as relevant to you. So finally, in Artemis specifically, there are lots of neat things we could do given the number of cameras that will be on different platforms, including on astronaut suits. So ASAS-CRATERS could be used to leverage these cameras to do local terrain analysis and data aggregation in real time to support crewed and robotic exploration in cooperation. For one example is that if an astronaut is doing an EVA focused on one particular task, but their camera feed is still taking in imagery, an astronaut that's not focused on those terrain features, the software could alert the astronaut, could automatically kind of detect features of interest and alert the astronaut if like a novelty feature of interest is detected in the images beyond what the astronaut is actually looking at actively. Beyond the moon, we have lots of other applications that we're interested in all over the solar system too. And I'll just wrap up by giving a shout out to our team. This project's been funded by the Canadian Space Agency, and I've listed our science team on the slide as well here. Of course, we're very thankful to everyone for their input and some good work on this project. So I'll leave it there and just thank you very much for your attention.
Okay, great, thank you. We have a couple questions in the chat. First one up is from Jeff Gillis Davis. How does this tool compare to the rover science autonomy using hypothesis mapping? There was a talk yesterday by Elder Noah Dobera on hypothesis maps. So you have a comment, and then you have some follow-up questions as well.
Yeah, yes, we're wondering that as well. We heard that talk and we're not sure, but we definitely want to follow up and chat and see where there might be some interesting overlap. I think there could be some good synergy there.